So, welcome to our continuing discussion of dimensional analysis and dimensionless groups. Okay. So, I would start off defining for you the dimensions and units, the fundamental dimensions, there are 6 of those, and the derived dimensions. So, all other quantities can be derived in terms of those 6 fundamental dimensions. The fundamental dimensions are mass, length, time, temperature, current and light intensity, and we had seen how to get the dimensions of other quantities in terms of these fundamental dimensions, okay, whether they were mechanical quantities, thermal quantities or electrical quantities. Okay. And last class we had got the dimensions of some electrical quantities, and I also said that equations have dimension. Okay. If you expand out the equation so that it is a sum of multiple terms, each term in that equation has to have exactly that same dimension. That is the dimension of the equation. Derivatives have dimension, they are proportional to the inverse of the quantity that you are taking the derivative with respect to. Spatial derivative has dimensions of length inverse, time derivative has dimensions of time inverse, integrals have dimensions, spatial integral has dimensions of length, time integral has dimensions of time. Okay. And we saw how to get the dimensions of an equation, the dimensions of the gradient operator, which also has dimensions of length inverse, and the dimension of a vector is the same as the dimension of each of its components, and the unit vectors have no dimension. Okay. So, now we will start our discussion of dimensionless groups. If a problem involves n dimensional quantities, okay, which are all related to each other, okay, in that through equation in that problem, okay, and that has m dimensions. Let me write that as fundamental dimensions. That relationship can be equivalently written as a relationship between n minus m dimensionless groups. Okay. So, for example, if n is 7 and m is 4, right, the original problem had 7 parameters, and so if you wanted to find a relationship, you would have to vary each of those 7 parameters independently to find out what is the relationship. But if there are 4 fundamental dimensions, I can reduce it to just 3 dimensionless groups. Okay. So, that significantly simplifies the relationship in the problem. Okay. So, that is the big advantage of okay, just cut that. Or we will start again.
Continue, sir.
No, will you be able to remove that in intermediate?
Sir, I can continue, sir.
Yeah, okay. Okay. So, that is equivalent to a relationship between n minus m dimensionless groups. So, there are only 3 dimensionless groups, okay, in this problem. So, I can easily solve the problem, find out the relationship by varying the 3 dimensionless groups rather than by varying all the dimensions. The quantities in a problem can be broadly divided into 2 parts. Okay. One is what are called independent quantities. Okay. Those are the quantities that are specified in the problem. Okay. Those are the quantities that can be varied in the problem, and the dependent quantity. which is usually only one quantity, which is the quantity that you want to find out, okay, in this problem. Okay. So, let us examine this by looking at an example. Okay. So, I have the problem of a sphere settling in a fluid. Okay. The sphere is settling in a fluid with some velocity v. Okay. The diameter of the sphere is d, and mass m. Okay. In a tank with some characteristic length L. Okay. Now, if you write the Newton's law for this spherical particle, basically what it will say is that mass times the acceleration dV by dt is the sum of the forces. Okay. Forces are of different types. One is the gravitational force, okay, that is acting on the sphere, which is mass times the gravitational acceleration, okay, minus the force of buoyancy, okay, due to the fluid that is displaced by this object, is basically equal to the product of the mass of fluid displaced times the acceleration due to gravity. There is a third force, which is the drag force. Okay. The drag force is because as the fluid flows around the particle, right, there is a flow field that is generated, and fluid friction causes a force to causes a force which is exerted on the surface of this object, and that force tends to reduce the velocity or decelerate the object. Okay. That is the drag force, okay, due to the fluid flow around the object. And we would like to know how the drag force depends upon the fluid properties, the dimension of the object, and the speed at which it is moving, as well as dimension of the tank and so on. Okay. So, the objective here is to calculate the relationship for the drag force on an object, okay, moving in a fluid. Okay. So, the drag force will depend upon the characteristics of the object. Okay. For example, in this case it is a sphere, so it will depend upon the diameter of the sphere. Okay. It could depend upon the characteristic length of the tank, okay, and the velocity, of course. Okay. And there is a drag force because the fluid is moving relative to the object. Okay. So, therefore, the drag force has to depend upon the flow properties of the fluid. Okay. And the two flow properties of the fluid are the density and the viscosity. Okay. So, these are the independent parameters. Okay. So, these are the independent parameters. And the dependent parameter is the drag force. Ft. The dependent parameter that we want to calculate, okay, what we want to know is what is the value of the drag force and how does it depend upon all of these other parameters. Okay. So, let us look at the dimensions of each of these. Okay. The diameter has dimensions of length, the length has dimensions of length, the velocity has dimensions of length per unit time, density is mass per unit length volume. Okay. m L power minus 3 is the density, mass per unit volume. Viscosity has dimensions of m L inverse T inverse, okay, and the drag force is a force. So, it has dimensions of m L square L T power minus 2 mass times acceleration is the drag force. Okay. So, in this problem there are 1, 2, 3, 4, 5 independent dimensional parameters, one dependent dimensional parameter, that is the drag force. Okay. And in general we can write the drag force as some function of L, d, v, rho and mu. Okay. So, you can see that these there are 5 independent dimensional parameters, one dependent dimensional parameter, and they all depend upon 3 dimensions, mass, length and time. Okay. So, therefore, you should be able to reduce them, right, to just one dimensionless independent parameter. So, in this case n is equal to 5 independent plus 1 dependent, that is total of 6. There are 3 dimensions and you should be able to reduce this to a relationship between just one independent dimensionless group and one and 2 dependent between one dependent dimensionless group that involves the drag force and 2 independent dimensionless groups. Okay. So, that is the objective. Okay. So, how do we define the independent dimensionless groups and the dependent dimensionless groups? The independent dimensionless, the dependent dimensionless group that involves the drag force, okay, has to be the drag force divided by some combination of these quantities which has the same dimension as force. Okay. It should be divided by some combination of these quantities which has the same dimension as force. Okay. And you can see that force has a mass dimension and density and viscosity has a mass dimension. So, therefore, you can scale the force by either the density or the viscosity. Okay. Which one you choose is subjective. Okay. We will see a little later. Where viscous forces are much larger than inertial forces, we will scale it by viscosity. Where inertial forces are much larger, we will scale it by density. But in either case, for the present, we will choose the viscosity as the scaling for the force. Okay. So, I will define my first dependent dimensionless group, okay, as a scaled drag force. The asterisk denotes that it is dimensionless, is equal to the drag force. Okay, I should put a capital. Okay, times it has to be scaled by something with mass dimension, either the density or the viscosity. In this case, I will choose the viscosity to unknown power a. Okay. And then it has also got to depend upon the length scale and the velocity. Okay. So, I will choose velocity power b and the diameter power c, okay, where a, b and c are as yet unknown exponents, okay, which will be determined from dimensional consistency. That is that the left side of this expression is a dimensionless, okay, quantity. So, it has no mass, length or time dimension. Okay, the left hand side is dimensionless, it is a dimensionless force. So, it has no mass, length or time dimension. On the right hand side, the force has dimension m, l, t power minus 2. Okay. The viscosity power a. Okay. Power a, velocity power b, L T inverse power b times L power c. Okay. For this equation to be valid, the sum of the exponents of each of these fundamental dimensions, mass, length and time, on the two sides has to be exactly the same. Okay. For this equation to be valid, the sum of the exponents of each term has to be the same on the left and the right side. Okay. So, if I take the mass dimension for example, okay, I have 0 on the left side is equal to 1 for force plus a for viscosity. Okay. If I take the length dimension, on the left side it is 0, okay. On the right side, force has exponent 1. In viscosity I have minus a, okay. In velocity I have plus b, and in the length scale I have plus c, okay. That is for the length dimension. And for the time dimension, 0 is on the left side. I have minus 2 as the exponent in the force, okay. In viscosity I have minus a, okay, and in velocity I have minus b, okay. So, these are the relations that have to be satisfied by the exponents a, b and c, so that the dimensions on both sides of all the fundamental dimensional quantities are the same, okay. And I have 3 equations for 3 unknowns a, b and c, and I can solve these, okay. The first equation will straight away give me that a is equal to minus 1, okay. I substitute a is equal to minus 1 in this equation, and I will get b equals minus 1, and I substitute that into this equation for the length, and I will get c equals minus 1. Okay. That you can easily verify. Okay. So, therefore, the dimensionless force is equal to F by mu v t, okay, when it is scaled by viscosity. Okay, that is the dimensionless force, that is the dependent dimensionless group. Okay, that is the dependent dimensionless group. Now, this dependent dimensionless group has to be a function of an independent dimensionless group. Okay. That independent dimensionless group has to or rather it has to be a function of 2 independent dimensionless groups, because I had total of 5 parameters and 3 dimensions between them. That means that the number of independent dimensionless groups has to be 5 minus 3, that is 2. Okay. One of these is easy to see, okay, because the diameter and the system size have exactly the same dimension. Okay. Therefore, one of the independent dimensionless group I can straight away get, which is L by d, the ratio of the tank size and the particle size. Okay. If L by d is very large, of course, you would expect the local flow around the particle to not depend upon L by d, but in general it can depend on this. Okay. And then there is another independent dimensionless group, okay, which involves the density and the viscosity. Okay. Both have mass dimension. Okay. So, therefore, I can construct this independent dimensionless group from the density, viscosity, the velocity and a length scale. In this case, I choose the length scale as the particle diameter, okay, for constructing this independent dimensionless group. Okay. And in the equation for the independent dimensionless group, I can select the exponent of any one of those as 1. Okay. The reason is because if I have a dimensionless group phi, say, okay, if phi is a dimensionless group, it implies that any power of phi, whether it is phi square, phi cubed, phi power n, they are all dimensionless groups, okay, phi inverse and so on. Okay. Similarly, if I have 2 dimensionless group phi and psi, it implies that any combination of these phi times psi or phi by psi and so on, these are also dimensionless. Okay. So, the definition of dimensionless groups is non-unique, okay, and to make it unique you have to specify the exponent of any one of those quantities. Okay. So, let us construct this dimensionless group, okay, by specifying that it has to have density to the first power. Okay. If I want density to some other power, I will just take some power of this dimensionless group, okay, but I will just take density to the first power times the viscosity power A, the velocity power B, and the length scale power C. Okay. This is a dimensionless group. Okay. For dimensional consistency, m power 0, L power 0, T power 0 is equal to m L power minus 3, the dimension of density, m L inverse T inverse is the dimension of viscosity. Okay, we had seen that previously. Dimension of viscosity is m L inverse T inverse power A. Dimension of velocity L T inverse power B and L power C. Okay. So, that is the independent dimensionless group, okay, which involves the density, the viscosity and so on. Okay. And we can find out the exponents in each of these, okay, just from dimensional analysis, that the exponents of the fundamental dimensions on both sides have to be the same. Okay. So, for the mass dimension in this case, I get 0 is equal to 1 plus A, okay, because only the density and the viscosity involve the mass dimension. Length, okay, 0 is equal to minus 3 from the density, okay, minus A from the viscosity, plus B from the velocity and plus C from the diameter. Okay. And the time dimension 0 equals, okay, minus A from the viscosity minus B from the velocity. Once again, 3 equations, 3 unknowns can be solved. The first equation can be solved to get A is equal to minus 1. Third equation can be solved to get B is equal to plus 1, okay, because minus A minus B has to be 0. And substituting both into this, we will get basically that C is equal to plus 1. Okay. Therefore, this dimensionless group is equal to rho V d by mu. Okay. It goes by the name of the Reynolds number. Okay. This is the ratio of the viscous and the inertial effects in the numerator. Inertia is proportional to density, because inertia is the is related to the mass of the fluid. So, as the density increases, the inertia increases, and viscous stresses are proportional to the viscosity, which is in the denominator. So, this is the ratio of inertia and viscosity. Okay. So, that is the second dimensionless group, and I told you here that there is total of 2 independent dimensionless groups. And 1 dependent. Okay, dimensionless group. Okay. So, we now have got our relation between these two. Okay. So, the dependent dimensionless group, okay, f star d, okay, is equal to f by mu v d is equal to some function of L by d and the Reynolds number. Recall, when we had originally posed the problem, right, we had wanted to calculate the drag force. Okay. The drag force was a function of 5 different dimensional parameters: diameter, length, viscosity, density, viscosity, velocity. Okay. So, there is a relationship between one dependent dimensional group, the drag force, and 5 independent dimensionless groups, parameters. Okay. By dimensional analysis, we have reduced this to a relationship between one dependent dimensionless group, which is the scaled drag force, non-dimensional drag force, as a function of 2 independent dimensionless groups, that is the ratio of lengths and the Reynolds number in this case. Okay. So, that is the power of dimensional analysis. It has reduced the dependencies in the problem. Okay. We know that the dependence of the drag force on these parameters can be only of this particular specific form. Okay. It cannot take any form. Okay. It can take only this particular specific form. Okay. Of course, beyond this we cannot determine the drag force from dimensional analysis. Either you have to do experiments in order to find out what this relationship is. The advantage with dimensional analysis is that the parameters that you have to vary in experiments is now only 2. It is not the 5 parameters you had in the original problem. Okay. Or you have to do some analysis and do the calculation. Okay. We can do a little more as far as this is concerned. Okay. So, first of all, if the particle diameter, okay, if the particle diameter is much smaller than the length of the tank, okay, if the particle, let us assume that you have a small particle in a very large tank. Okay. In that case, the flow field around the particle locally, okay, on a scale comparable to the particle diameter, okay, will not be affected by the boundaries of the fluid, which are very far away, okay, compared to the particle diameter. Okay. So, because the boundaries are very far away, you would expect L not to be a parameter. Okay. So, if a particle was settling in an infinite medium, then the length is no longer a parameter, and therefore, this parameter L by d is no longer a parameter in the problem. Okay. So, in that case, this L by d is no longer a parameter. Of course, if you are in a small tank, then of course, it does depend upon the dimension of the tank. The other thing that you can infer is that Reynolds number is the ratio of inertia and viscosity. If the Reynolds number is small, okay, if the Reynolds number is small compared to 1, that means that inertial effects are negligible compared to viscous effects. Okay. In that case, the drag force cannot depend upon the density. Okay. If inertial effects are small, the drag force cannot depend on the density. That means that it has to depend only upon the viscosity, the velocity and the diameter, and in that case you get an equation for the drag force, which is basically F by mu v d is equal to a constant, okay, because it no longer depends on the density. So, density is no longer an input to the dimensional analysis, and if density is no longer an input, the only other parameters that are there are the viscosity, velocity and diameter, and this is the only way that the force can depend on the viscosity, the velocity and the diameter. What the value of this constant, we do not know. Okay. You need more detailed calculations for that. More detailed calculations actually tell us that this constant is actually equal to 3 pi. Okay. This is called Stokes' law for viscosity for a spherical particle. Okay. You can actually calculate that. This is outside the scope of this course, so we will not be able to do it. But just using dimensional analysis, we inferred that this ratio has to be a constant. Okay. What when the Reynolds number is large? Okay. In that case, the viscosity can no longer be a parameter. Okay. If we assume that viscous effects do not determine the drag force on the particle, then the viscosity is no longer a parameter. Okay. And what that means is that the drag force has to depend only upon the density and the velocity and the diameter. Okay. Okay. In that case, the drag force scaled by inertial scales, okay, you have to go through the dimensional analysis again, okay, the same analysis that we had done over here. Okay. The same analysis that we had done over here to get this equation for the drag force. That analysis you have to do, but now including the density instead of the viscosity, okay, to define the drag force. And if you do that, it is quite easy to do in a similar procedure. I will not go through the details. What you will get is that this drag force divided by rho v square d square. Okay. You can verify that this is dimensionless. The force on top is m L t power minus 2, and the denominator I have m L power minus 3 into L square t power minus 2, that is the velocity square into L square. Okay. And this you can verify for yourself that it is dimensionless. You can do it by having unknown exponents and then getting the equations and so on, but since this is straightforward, I already know the answer. So, this will be the drag force as defined by based on inertial effects. And you would expect that this has to be a constant if viscosity is not important. Okay. The Reynolds number is large, viscosity is not important, then this would be a constant. Okay. What is usually defined for these problems is as the non-dimensional pressure is what is called a drag coefficient. Okay, so let me the drag coefficient for an object moving relative to a fluid. Okay. So, if I have an object that is moving relative to the fluid with some velocity v, okay. Now, the area projected, okay, along the flow direction, this cross sectional area that is projected along the flow direction, okay, is called the projected area, and rather than writing a correlation for the drag force itself, you write a correlation for the average pressure on the projected area. Okay. So, you write an equation for the drag force divided by the projected area, okay, which is like an average pressure acting on the surface. Okay. Note that the pressure acts perpendicular to the surface. So, the area that you take for calculating the pressure force is going to be the projected area, not the surface area. Okay. And this drag coefficient is a scaled force divided by projected area. Okay. And you can easily verify that a force per projected area has dimensions of pressure, because pressure is force per unit area, and this is divided by half rho v square. Okay. Half rho v square is effectively a kinetic energy per unit volume. Okay. So, the drag force is usually written for that. Okay. That is the drag coefficient that is defined, the non-dimensional drag coefficient. Okay. And the drag force is the correlation for the drag force is written in terms of this. I will say a few more things about the drag force on an object in the next lecture, and then I will proceed to solve some more examples of using dimensional analysis for calculating the forces and other quantities in other problems. Okay. So, we will just discuss a little bit about this drag force and then come back and go on to other topics in the next lecture. I will see you then.